Hello and welcome to the Unit 9 Section 1 video on identifying exponentials. So in the last unit we talked all about quadratic functions, how we identify what a quadratic function is, how we identify the key features, how we graph it, and how we work with it. Well, we're going to do the same thing in this unit, except we're going to do it with exponential functions. So let's talk about what an exponential function is. Take a look at this example. The table and graph show an insect population that increases over time. So at the first start, we have a population of 2. Okay, we have 2 insects. After 1 day passes, we are now up to 6. Then after 2 days, we're up to 18. And then after 3 days, we're up to 54. We can create a function that describes this data, first of all, by creating the graph that you see here. And you can see that the data is growing rapidly, especially as we get to days 2 and 3. And the number that we're getting, we're growing it faster and faster with each day. So a function rule that describes that pattern is 2 times 3 to the x power. This type of function in which the independent variable, or your x, appears as the exponent is called an exponential function. Okay, so notice that the 2 that you have out in front is your starting population, and 3 is the amount by which the population is multiplied each day, because 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54. So we're going to keep revisiting this idea of where our starting value goes and where our amount that we're multiplied by is positioned as well. So the definition of an exponential function is a function of the form f of x equals ab to the x, where a is not equal to 0, b is not equal to 1, and b is greater than 0. Okay? So to identify an exponential equation has to have a variable in the exponent, and the base cannot be 1. As long as those two things are met, then we have an exponential equation. So let's take a look at a few exponential equations and see if we can identify which ones are exponential and which ones are not. So in A here, we have a variable in the exponent. So since there is a variable in the exponent, it is exponential. In B, there is no variable in the exponent. In fact, there are no exponents at all, so this is not exponential. For C, we have an exponent, but the exponent is 2. We have an x squared, so this one, not exponential. In D, we do have a variable in the exponent. We have 3 to the x, so it is exponential. For E, no exponent, so certainly not exponential. For F, we have 1/2 to the x. The power is the x, so it is exponential. For G, the only power here is 2. 2 is not a variable, so it's not exponential. For H, we have 1/3 to the x. X is in your exponent, so it is exponential. Same thing for I. X is in the exponent. For J, we have no exponents, so not exponential. If you have no exponents at all, that certainly helps clear things up a lot faster here. In K, we have 5 to the x, so the x is in the exponent, so it's exponential. And then L, remember, your base cannot be 1. Here, our base is 1, so it's not exponential. And the reason for that is 1 to the second power is just 1. 1 to the third power is just 1. 1 to the 5,000th power is just 1. So we don't have an exponential function because there's no growth to this function. There's also no decay to this function. Those are two terms that we're going to be talking about here in a little bit. But the bottom line is the function doesn't change depending on your value of x. So 1 to the x is actually a constant function because it's always going to be 1. All right, let's talk about exponential graphs. The graph of an exponential function features an increasingly small y values on one side of the graph and increasingly larger y values on the other side of the graph. Exponential graphs follow the general shape shown here, but can be oriented differently. So you can flip it upside down, you can flip it from left to right. So You just need that general shape. So let's see if we can identify a few exponential functions using graphs. So in A, we have that growth. It's very little on one side, and then it's a lot on the other side. So that one is exponential. B, obviously not exponential. It's a straight line. C, we recognize that shape as a parabola, so that is not exponential. D, we have that general shape again, growing very slowly on this side, growing very quickly on the other side, except in this case, we're actually not growing, we're going more negative. But it does have that shape, so it is exponential. Same thing for E. We're growing very little on this side, growing a lot on this side, so it's exponential. And then F, we just have a couple of straight lines. This is actually, for those of you who don't know this yet, this is an absolute value function, so it's not exponential. Now talking about exponential tables in ordered pairs. Remember that linear functions have a constant first difference, and a quadratic function has a constant second difference. Exponential functions do not have constant differences, but they do have constant ratios, which means each time we change our x value by a constant amount, we are going to multiply our y values by a constant amount, okay? And of course, these constant ratios, this constant ratio here is your b value in your exponential equation. So let's determine if this table of values represents an exponential function. So first we check our x's. We do have a constant change in x. We add 1 each time. Then in our y, let's check out what our ratios are. So the best way to do this is to take the second y value and divide it by the one that comes before it. Okay, so we're going to do 3 divided by 1.5, and that's 2. So our constant ratio is times 2, or our ratio, at least for these two, are. Okay, so 1.5 times 2 gives you 3. 3 times 2 gives you 6. 6 times 2 gives you 12. So since we have a constant ratio, we're multiplying by 2 each time, we do have an exponential. For B, well, let's check here. First of all, we're adding 2, and this is where I actually have a typo, okay? This should actually be plus 1, not minus 1, so plus 1 here. So I'm going to kind of put my cursor there so it looks like plus 1. Then we go from plus 1 to 3, and then 3 to 5. So we're adding 2 each time. So on the other side, we have 9 divided by negative 9, which gives us negative 1. So we multiply by negative 1 to get to 9. Well, what do we multiply 9 by to get to 27? Actually, it's not 2, it's 3. So another typo here. And 27 to 45 is times 5/3. Despite all the typos, either way, this is not an exponential function. A set of ordered pairs is a set of x values with their corresponding y values. So to determine if a set of ordered pairs is exponential, you can simply write the ordered pairs in table format and then do what we just did to check your constant ratio. So in example 4 here, I'm going to pop my x and y values into the table from our sets of ordered pairs. We do have a constant change in x, so let's check our ratio. What times 1 gives me 0? That's 0. What times 0 gives me 1? Well, there is no number that exists. You can't multiply 0 by anything to get 1, because anything times 0 is 0. And just furthermore, 1 times 4 gives you 4. So obviously we do not have a constant ratio, so it is not exponential. For B, let's pop in our x and y values. Our x values change by 1 each time. So what do we multiply 4 by to get 2? Well, we can multiply it by 1/2. If you divide it by 2, it's the same as multiplying by 1/2. 1/2 of 2 gives me 1, and 1/2 of 1 gives me 0.5. So here, every time we're multiplying by 1/2, so we have a constant ratio, so it is exponential. Now let's talk about identifying exponentials in the real world. Similar to linear and quadratic functions, we can identify these things. You can model a real-world exponential relationship by identifying the values of a and b in the function. Okay, so we know that a, we talked about this a little earlier, a is our starting value and b is our constant ratio. In fact, in a real-world situation, we may not even need to have a starting value. We just need to know that whatever we're starting with changes by a constant ratio, unless that starting value happens to be 1. But of course, that would be specified, okay? You need to know what the constant ratio is, but this may not be given numerically, okay? It may be given as some sort of word, like something doubles. If something doubles, you're multiplying by 2. Or if something triples, you're multiplying by 3. Or if something is halved, you know we're multiplying by 1/2. Okay? So you got to look for those key words as we go through these. So let's determine if each real-world scenario would be modeled by an exponential function. So for A, the population of town A is 800. It grows by 5% each month. So we know our starting value is 800. That's our A value. And we know that it's changing by 5% each month. Now, be careful here because our change is 1.05. That's what we're going to multiply by each month because we're growing here, okay? So that means that we're keeping the original 800 and we're adding another 5% on top of that. So that's 1 plus 0.05, which is 1.05, okay? And that's what we're going to multiply by each month. So this is an exponential function. The population of town B is 500 and it grows by 40 each month. Well, here we have a starting value of 500, but we're changing by 40 each month. Okay, we're adding 40. We're not multiplying by 40, we're adding 40. And because we're adding and not multiplying, this is not an exponential function. For C, the number of bacteria in a sample doubles every hour. We don't know what our starting value is, but as long as it's not 1, we know that we're doubling it every hour, so it's changing by 2, or multiplication factor of 2, which means we do have an exponential function. The amount of radiation coming from a sample, given that the amount decreases by half each hour. We don't know what our starting value is, but we know we're decreasing by half each hour, so we're multiplying by 1/2, so we do have an exponential function. In E, the total cost of stamps given that each stamp costs 48 cents. Well, here we can create a function, and we can pull our old linear function skills out, okay? Because we know each stamp costs 48 cents. You multiply 48 cents by the number of stamps you're going to get, and that gives you the total cost. Well, that we already recognize as linear, so therefore it is not exponential. The total mass of a box of baseballs depends on the number of baseballs in the box plus the mass of the box. So we've got the mass of the box, and then we're adding 1 baseball each time. Here we're not multiplying, we're adding, so therefore it's not exponential. And then finally, a microbiologist started a lab culture with 25 cells. The number of cells doubles every 4 hours. We start with 25. We double it every 4 hours, so we're multiplying it by 2. So therefore, we do have an exponential function. So here we're just trying to get you comfortable with recognizing what is going to be an exponential function when presented with a real-world scenario, because a little bit later in this unit, you're going to actually take this information, which we've already identified, and you're going to create an equation and then answer some things based off of that equation that you create. All right, we're going to wrap up this section with one final thing that I want to talk about, and that is growth and decay. This is something that is unique to exponential functions, okay? So if you're asked if a function has growth or decay, you can only answer that for an exponential function, Okay, so if you have a function that's non-exponential, you are not going to answer whether or not you have growth or decay. Exponential growth occurs when the quantity increases by the same rate for each unit of time, okay, by that same constant ratio. Exponential decay occurs when the quantity decreases by the same rate for each unit of time. So to determine if an equation or a table represents exponential growth or exponential decay, you want to look at the constant ratio, which is your b value. If b is greater than 1, then you have growth. If b is between 0 and 1, then you have decay. So if your b value is like 1/2, 1/3, 2/3 even, okay? A graph representing an exponential growth will increase from left to right. A graph representing exponential decay will decrease from left to right. And there's examples of that. So real-world situations will more explicitly state whether we have growth or decay occurring. So let's take a look at example 6 here. We're going to determine if exponential function here, so all these are exponential functions, demonstrate growth or decay. So let's take a look at A. Our b value is what we're looking at. Well, our b value is 3. Since that is greater than 1, then we have growth. For b, our b value is 1/3. That is between 0 and 1, so we have decay. For c, our b value is 0.28. That is less than 1, greater than 0, so we have decay. For d, our b value is 1.78. That's greater than 1, so you have growth. For e, well, from left to right, that graph is increasing the entire time, so we have growth. And in f, from left to right, that graph is decreasing the entire time from left to right, so we have decay. All right, so that finishes off this section, introducing you to exponential functions. How do we recognize exponential functions? Coming up in the next section, we are going to talk a little bit about the key features of exponential functions. How do you identify those key features?